Good morning and welcome to the ShanghAI lecture. Welcome to this fifth lecture, today from the Biorobotics Institute of the Scuola Superiore Sant'Anna in Italy. It is the fifth of the ShanghAI lectures in this year program. It's on soft robotics. And the program for today is, after this quick welcome, a few words from Fabio Bonsignorio from Tokyo, and then we will have our first lecture by Danica Kragic from scene segmentation to task-based grasping, and then we will have a short coffee break. Two more lectures will follow, one by myself, Cecilia Lasky, how an octopus robot can help building a robot. And then Bram Vanderborg about hard work for robotics from soft actuators. And we will wrap up the lecture at 11:30. You know how to interact already, maybe, but you can raise your hand if you are in a video conference participating inside, or you can use the question board, the Facebook page, or Twitter. So let's now hear from Fabio. He's hello from Tokyo.
Hello from Tokyo. I am here at the University of Tokyo. Kindly hosted by Professor Kuniyoshi, which is by the way not here. So I just want to welcome and to thank everybody for continuing participation in this experiment. I mean, you know that we are pushing a kind of radical, with Rolf, following Rolf's example, we are pushing a kind of radical stance on embodied cognition. You also know that it's not so easy. It's an open project. It's work, but a lot of work has to be done. And actually, this is we are already in the middle, and this is the first of a couple of lectures on two tightly related topics, which are soft robotics and bioinspiration. Actually, with respect to previous editions, we are trying to be a bit syncretic, because we, for instance, the approach that Danica will present, which is a very successful and what you could expect from Danica. I mean, it's a nice, it's a good approach. It's actually is not completely, if you want, mapped on the view that you can derive from how the body shapes your. But I mean, we are researching, so of course there is a piece of truth on many different on the work of many. I mean, this is a community effort. So welcome from Tokyo, and I don't take any more time. Bye.
Okay, so welcome back. We are ready to go on with the next lecture, which is given by myself. I'm Cecilia Lasky from the Biorobotics Institute of the Scuola Superiore Sant'Anna. And this is one of the lectures on soft robotics and bioinspiration, number 1. And the title is How an Octopus Can Help Building a Robot. So in my lecture, I will start from a little bit from the beginning of robotics, and I will outline how the evolution of robotics brought the need for bioinspiration at a given point, and this bioinspiration somehow brought the need for soft bodies. And then we have a need for some different novel techniques for controlling such soft bodies. Then we will
Cecilia, I'm sorry. Do you want to play your slides full screen?
Yes, sure. Sorry.
Okay, thank you.
And we will see what an octopus can teach us when we want to build and control and soft robots. We will see the magic of muscular hydrostat and embodied intelligence in the octopus. Then we will see a specific case, the case of our octopus robot, to see how we can go from biology to robotics. And I will close the lecture with some view of unexpected applications for octopus robots. And I just quickly say my conclusions about the momentum that soft robotics has now and how this community can grow. So I was saying that I started from the very beginning of robotics. We all recognize industrial robotics as the start for all the techniques and theories for robot control. And we know that the main issue here is that the environment is structured. Then we know that pretty soon roboticists wanted to start apply robots in services instead. So here the environment is unstructured, and there is a need for more techniques for controlling robots, techniques that control the behavior of the robot, so perception and action loops. And of course, if the problem is that the environment is unstructured, that the robot has to manage the real-world environment, then biological systems represent an excellent source of inspiration. And we see several examples in literature of same service tasks solved with bio-inspired solutions. But as I said, this bio-inspiration brings with it a need for soft robot bodies. This is a clear difference we see in traditional robots and biological systems like animals or plants. And this is a nice example of a robot built with an inspiration to the cockroach by Mark Atkowski at Stanford, where the nice solution that is bringing this robot to be very, very fast is a compliant part in the legs, a compliant joint in the leg. That is the key principle by which the cockroach itself can be so fast, because this compliance gives a reaction that is given just by the mechanical structure, a reaction to the contact with terrain. And it's also a nice example of new fabrication techniques that allow these soft parts to be integrated in robots. But if we go back to what we learned about robotics in our university courses, we know that every handbook, textbook on robotics say that a robot is a chain of rigid links, of rigid bodies. And all the kinematics for robots start from this very basic fundamental definition, chain of rigid links. So what happens if we don't have such rigid links? So if we have a soft robot, how to control a soft robot? Well, the octopus can teach us a lot. First thing is that it's if we can have the first video, it is very clear that the octopus can tell us, well, we don't really need bones or other rigid structure in our body. The octopus, in fact, is a special animal in having absolutely no rigid parts. So only soft tissues, mainly muscular tissues. And this is pretty clear. But at the same time, without bones, so the octopus can tell us, well, I still can apply very high forces. So a lesson to robotics is that we don't need bones for being strong and for doing manipulation or locomotion. You see here the octopus opening a living shell. So you know there are very high forces needed here for this task. Then what they also teach us is that we don't need much processing for this control. We don't need a very large brain. In fact, the octopus brain, the octopus is a mollusk, so in general they have a pretty reduced nervous system and especially very reduced brain. Within the mollusks, the cephalopods and the octopus especially have a pretty high number of neurons. But still, if you see the central nervous system, we talk about 50 millions of neurons. So we have many neurons more in the arms. So this tells us that we don't need much processing at the central level, the brain level. We probably need a lot of processing also at the peripheral level. So control is highly distributed here. And what are the octopus solutions for being so strong without bones? It's the muscular hydrostat. The muscular hydrostats are very special muscular structures. You find them in the octopus and in the tongues of mammals and in elephant trunks only. And they can be considered as modifiable skeletons with variable stiffness. This is the key. In fact, they are composed of muscles arranged along different directions. So we have main muscles arranged longitudinally in the arm and transversally in the arm. And the combination of their contractions can give all the different bendings and deformation of the arm that we can observe in the animal. But especially the co-contraction of these two kinds of muscle can stiffen the structure. So what's interesting here for robotics is that in fact this muscular structure made of soft tissues can stiffen. And in this sense, we can see the muscular hydrostat as a modifiable skeleton. There are also oblique muscles wrapped around the arm that are mainly for torsion. And the second solution that we can take from the octopus is that the control is distributed and the properties, the physical, the mechanical properties of the body are exploited by the animal in control. If you can have a look at the next video, we can see first how an octopus outside of its environment, which is water, is not so well performant. So you see that the movements of the arms here are very difficult. So it's a sort of evidence that the interaction with water is important for the arm movements. And in the next video, we see a very simple test that we made. This is a simple arm is even too much, silicone cone. And there are some similarities with the octopus. One is the density, it's the same density. And the second is the geometry. This geometry is roughly the geometry of an octopus arm. And it is in water. So if you observe the reaching movement in the octopus, you see that they have this wave of bending from the proximal to the distal part of the arm. And if you observe what happens to our passive arm when you apply an acceleration at the base, you see a shape, a deformation that is very similar to the reaching wave, bending wave of the octopus. So you can conclude that a big part of the control of that reaching movement is done by the mechanical properties. Here you see how the octopus tend to lay the arms along the surface of water, and we thought it was controlled not to go out in the air, but in fact it is exactly what happens passively to our simple silicon arm. So again, this movement, this behavior is not really controlled by the octopus, but it's somehow given by the mechanical properties. So now we have many lessons from the octopus, but the difficult part is going from the biology to robotics. And we have to take into account that the solutions we find in nature are given by evolution. And evolution is based on natural selection, which is not engineering. So what we observe in nature are solutions that came out from changes of the environment that required for different solutions in the animal, but in this sense they are never the optimal solution. So we must be very careful in copying nature. We should not just copy, but we have to identify the key principles that work well in the animal or in the biological model in general for a given task in a given environment, and we should try to extract the principle and implement the principle in robotics. So what is special in the octopus in this sense? Well, in the roboticist eyes, what's really interesting is that we can have the three main tasks we want in robotics, in robots, so manipulation, locomotion, and swimming. For manipulation, we already saw that the special thing is the muscular hydrostat, but we had to measure some of the feature, the mechanical characteristics of the arm and also some anatomy. From a mechanical point of view, what is really impressive for a roboticist is the fact that the arm can elongate very much thanks to the contraction of the transverse muscles when the longitudinal muscles are relaxed. And we could measure up to 70% of elongation in our animals. And also the force they can apply with one arm is pretty interesting, because they can reach 40 newtons with just one arm. Fortunately, you see they are not very fast animal, because the contraction time is between 1 and 2 seconds. Then the anatomy is also very interesting, and we could, observing the animal, we could understand how to arrange the fibers of the transverse muscles and the longitudinal muscles especially, as well as understand how the nervous fiber could be inside the arm without being stretched during the elongations. In fact, they have a special arrangement, a sinusoidal arrangement that allow them to elongate in a sense. And I present just a summary. We derive our specifications from these measurements and observation. This is in the summary table, but there are publications on this. So finally, our octopus-like arm is based on transverse actuation that is realized with springs made of SMA, chain memory alloys. So you see on the left a picture of the inside of the arm where you see one layer of these springs that can reduce the diameter of the arm and consequently elongate the arm, so increase the length. The very basic structure of the arm is the braid. You see the external braid, which has a special geometry by which it can allow the deformations of the arm but still keeping the shape. And especially it can distribute the forces applied locally by the actuators to the rest of the arm. And in the video, if we can see the video, we can see how what are the movements that we can obtain. In this prototype, we have the transverse springs and cables that simulate the longitudinal muscles. Cables are of different lengths, so they are fixed at 1/3, 2/3, and the tip of the arm. So you see here the bending obtained by cable, but we can use cables at different lengths in the arm to obtain different curvatures, so curvatures in different directions. And we can see the shortening of the arm when we pull more cables together. The elongation instead is given by the contraction of the SMA springs transversally. And this is just an example of grasping. Okay. Then, as I said, another interesting task that the octopus can do is locomotion. Here we had again to make observations of the animal and measurements. The strategy for crawling for this locomotion was not clear to biologists too. And we observed the animal with a transparent bottom and a mirror to see which arms were used and which socket. If we can start the video, and now we can see the strategy that the octopus use. They use the back arms. And if you see here, they shorten one arm in the back, so it's a shortening phase. Then they attach this shortened arm to the bottom, and they push by elongating the arm. And then they detach and restart this full-phase mechanism. And this is very simple. What you need here is just the possibility to shorten and elongate, and also the capability to attach to the bottom, to the terrain. In this very simple prototype, we just have a silicone arm with a cable, and the friction of the silicone, the surface, is enough for attaching. And we reproduce this very simple mechanism. Then we try to reproduce these 4 phases with a very simple mechanism so that we can use just one motor. You see that with a flexible cable we can obtain a circular movement with the motor that is converted into the 4 phases of the locomotion strategy thanks to the soft material used for the arm. And we built our final octopus robot with 2 manipulation arms with the SMA springs as transverse muscles, and 6 arms with this shortening elongation capability for locomotion. And we can see here a short video of the final prototype in water. Again, all these prototypes work in water because we have to exploit the, let's say, the embodied intelligence of the octopus and of our robot, because the effect of water, of the interaction with water, changes completely the behavior of the manipulation arms and also of the locomotion arms. This is a simple task where we combine crawling with grasping. Then swimming is also very interesting in these animals, similar to what happens in other cephalopods. They used the so-called mantle to obtain jet propulsion. They can eject water from the mantle through a funnel, and they change the diameter, the volume of the mantle to have the water flowing in. And what's interesting here, there is, a lot of fluidodynamics that I'm not presenting, but what's interesting here is that the pulsation of the jet propulsion is, in the animal, is the more efficient one for propulsion, because it has the frequency that gives ring vortexes, so the best efficiency for propulsion. And we tried to build something similar to an octopus mantle, again with a soft material, with silicon, and we reproduced the possibility to reduce and increase the volume, internal volume of the mantle, by using cables actuated with one single motor. And again, we have a video showing a very first prototype that can swim by this pulse jet. From the engineering side, the choices here and the models here regarded the dimensions of the mantle and especially of the funnel, as well as the frequency of the pulsed jet. Okay, so you understand that the initial challenge was very general. So, can we build robots with soft materials without rigid links, which is what we learned at the university about robotics, and the octopus robot is a first answer to this. But the usual question I received, and I still receive, is what is it for? What can you do with an octopus robot? Why did you build a robot in the shape of an octopus? Of course, it's not a direct answer that I can give, but now that we solved some of the technological problems and we have some solutions, there are applications coming out, for example, in the biomedical field. So the knowledge, the know-how, the technologies gained in the octopus project are now used for building an endoscope in another project called the Stiff Flop, an endoscope that can change the stiffness. And the SMA actuation that we tested in octopus, with all the limitations that we know this technology have, is now the focus of an industrial project that we are carrying on with ST Microelectronics and SciSgetters, who are the providers, the suppliers of the SMA materials and springs. So it seems that even if in octopus we made the first test of the use of these actuators, it seems that they can become real actuators for soft robotics. And another very interesting field of application that we didn't really imagine before is the use of these technologies for realistic simulators of body parts. So medical doctors, when they see our octopus, which is soft and can move and can deform, they think that the same technology can be used for fabricating body parts that are simulator of the body parts they are interested in study, more realistic. And we already built a first prototype of the human larynx, a part of the human larynx, the vocal cords, and the lungs of preterm infants. A more natural application of these soft robotics technologies are marine applications, and we are going on still with an octopus-like robot that we want to propose for underwater tasks. So underwater robots are usually vehicles, either autonomous or remotely operated, and they are very good at monitoring tasks, at taking images and reaching high depths. They are not very good at those tasks where you need a safe contact with the environment. So usually they cannot get in contact with the sea floor or a coral reef or any other structure underwater. So that's why we think that we could propose a soft robotics approach to underwater robotics. And we are now carrying out this Poseidrone project, which is a local project where we want to see if a marine robot can operate, a soft robot can operate in contact with the sea bottom or other things with locomotion and grasping capabilities, because we have all these parts from the octopus experience. We know how to do grasping, we know how to do crawling, and even swimming with the pulse jet propulsion. So we have all these parts, and we are going to put all these parts together in this new robot here. The system is a little bit simplified. We don't have the focus is no more on the animal, so the biological inspiration is a little softer, I could say, but the application aspect is more important, and we aim at a robot that can go really on the seafloor and in small spaces. We can see a very first video of the first prototype, so the very first integration of only 4 arms, so you see here, and the mantle the mantle can do the pulse jet swimming. This is a test in a tank that we have, by the way, with salt water. It's not fresh water. Riesci a vedere? No, tu da internet.
I'm sorry for the bad quality of the video, but it's too large for the computer to handle.
Okay. Yeah, because there's a second part where the robot is really thrown in the water, in the sea, and when touching... okay. Are you trying again? Okay, so this is the test in the tank with salt water. And this is the swimming part. When in contact with the rocks, it can start crawling. Okay, we can go to the next one where we see the tests in the real sea. So you see that the robot is completely soft, very robust. You can really throw it into the water. It can then swim, as you see here, and again, when in contact with the rocks, it can start crawling. There is also a camera already integrated in the robot so that we can get images. Okay, so my concluding remarks, soft robotics is a growing field at international level. You see here, maybe it's a little bit difficult to read, but it's a plot of the number of publications in this area in the last year, and you see that there is a very clear increase. There is a community that is starting gathering in a very emergent way. And last year, the technical committee on soft robotics was established in the Robotics and Automation Society of the IEEE. And last month, a CA coordination action on soft robotics just started with the support of the FAT Open program. So I think it is the right moment now to invest in research in this area and to make this emerging community to consolidate and grow. So thank you for listening. Thanks, of course, to all the many people in the teams of the soft robotics group at the Biorobotics Institute, as well to the Octopus project, first of all, and the other projects that allow to do all these things. and including our octopuses, who were always very collaborative for our experiments. Thank you. Of course, if there are questions, it's now time for questions. I'll be happy to answer.
I may have a comment. Unfortunately, Danica, so Professor Kraj, left, so he's not here anymore, so it could be a bit unfair. But there is a big, I think that people will may have noticed it, that there is a big difference. Apparently, there is a big difference in the conceptual approach and in the topics of research in between you and Professor Krajcik. You know? So, I mean, on one side, you have data-driven machine learning approaches which actually are also complex systems. On the other side, there is this small engineering pieces of soft material put together and showing an emerging behavior. So, let's say my personal idea is not, I mean, these two talks were put together on purpose. Because actually maybe, I don't know what you think, Cecilia, about this, but I think that one of the big challenges is to bridge the big distance between the octopus and the grasping data-driven style. Right? I don't know what you think about it.
Yes, you're perfectly right. So in the Octopus project, we focused very much on the hardware. I mean, the hypothesis at the base was that the hardware was important, and the soft body was important, and so on. But the starting hypothesis was that it was important for building the intelligence, for having an intelligent behavior. So this is exactly the point. So for now, we had to develop the technologies for building the soft body parts, but we now have to add the intelligence, and it's a kind of intelligence based on the embodied intelligence approach, of course. So you're perfectly right. Now the two words of cognitive science or artificial intelligence or what else should meet with the soft robotics, which is still very much focused on the hardware, on the body wear. But yes, you're definitely right. I fully agree. Any other questions from the students? Maybe I see the students.
I'm from Madrid.
Okay.
Hello.
Hello.
Hello. I have a question. I would like to know how important is replicate an animal with 8 arms. For example, is important the 8 arms in the experiment? For example, why no 9 arms, 10 arms, 7 arms? How important is this?
Yeah, this is also a good question, because this is the question we made to the biologists at the beginning. So why 8 arms in the animal as well? And it is not clear if there is a special reason. This is also what I said with the slide where I said, be aware that natural evolution is not engineering, and the solutions you find in nature are not the optimal solutions. For example, we know about the octopus that in the past, the number of arms was even higher, maybe 12 or 10, and this number is reducing with evolution. So probably 8 is not the optimal number. It's where evolution arrived today. But we don't know if in the future the evolution will reduce again more than this, the number of arms. So from the engineering point of view, of course, having many arms give gives redundancy, which is important. We have some trials where we, for example, we lose some arms in the robot and the robot can continue working. So redundancy is one reason to have more arms. Probably 4 is enough for basic locomotion. Like in the first prototype of the new project that we built, 4 is enough for locomotion. Of course, you don't have much redundancy, you don't have much robustness, but then, I mean, I don't have an answer based on some optimality criteria for choosing the number of arms. That's a good point. Thanks.
Okay, thank you.
Okay.
Okay, we have one more question, this time from, if you have time.
Yeah, I think last question, I'm a little late on the schedule.
Okay, so this is a question from Philip. He's watching the stream from Berlin, and he's asking what are the general approaches in soft robotics to solve for problems like forward inverse kinematics, as you have to take the properties of soft materials like deformation, changing frictions, and so on into account? And what's the importance of these kind of exact models in soft robotics?
Yeah, okay, of course this is also a very good question too. I started my lecture with the problem of controlling these robots with the techniques we know. Of course, one answer is that we hope to exploit embodied intelligence and morphological computation to a level where we don't really need the control in the traditional sense. On the other side, we also made some works that I didn't present in my lecture about the modeling first and then the control of these soft structures. So, of course, it is very complex with more or less traditional mathematical tools, but it is possible. I mean, we have some results in modeling an arm made of silicon in a conical shape and actuated by cables. And with the result of modeling, we can have the forward kinetics, the inverse kinetics, and we could also develop a control system for it. Again, I didn't present this in the lecture, but it's the work by Renda and Dorelli that you can find in literature. So this is my answer. Okay, so I think we have to stop here. I'm sorry for taking a few minutes, even because we have another small talk by Dustin Lee on Brain-in-a-vat. It was not scheduled, but it's a short talk of 6-7 minutes, and I think it's very, very interesting from the title. So please, Dustin, go ahead.
Okay, is that okay now?
Yes, it's okay. You can start.
Okay, I will give you a brief introduction of a Brain-in-a-vat today, because I think this is asked by Rolf last lecture. So I will start from now. So first, imagine that a human being, you can imagine that to be ourselves, has been subjected to an evil scientist, and the person's brain, you can imagine that to be a brain has been removed from the body and placed in a vat of nutrients which can keep the brain alive. So the nerve endings have been connected to a super scientific computer, which causes the person whose brain it is to have the illusion that everything is perfectly normal. So radio 1 here, thank you. Nasa?
Equipment, weapons, training simulators, anything
So we can say that those people are already in a computer program, and there seem to be people, objects, and sky. But really, all you're experiencing is the result of electronic impulses traveling from the computer to the endings. So we do 2 here. Thank you. We do 2. This is 3.
Oh, sorry.
2.
What is real? How do you define real? If you're talking about what you can feel, what you can smell, what you taste and see, then real is simply electrical signals interpreted by your brain.
So how could it be possible to tell from the perspective of that brain whether it's in a skull or in a vat? So what does this mean? It means that you cannot be sure that whether your brain is in your vat or in your skull. And the world may be arranged to you. Your chair, a book, a table, your hands, and all things of the illusions. They come to this embodied brain with a super powerful computer. And the computer maybe is so clever that maybe if the person tries to raise his hand, the feedback from the computer will cause him to say and feel the hand being raised. And also, when we seem to have a communication, when I seem to myself to be talking to you, and when you seem to yourself to be hearing my words, maybe it's not that case. And maybe it's not the case that my words actually reach your ears. And maybe it's for you don't have real ears because you are a brain event, and nor do I have a real mouth or tongue. Rather, when I produce my words, what happens is that the impulses travel from my brain to the computer, and which causes me to hear my own voice uttering these words and feel my tongue moving. And also cause you to hear my words and see me speaking. And in this case, we're actually in communication. So it can even seem to the victim that he's sitting and reading this absurd and amusing story that there's an evil scientist who removes people's brain, just like that. For example, maybe I'm the victim and I'm reading these words about this amusing story, but maybe I'm just a brain event. So this classic storytelling was given by the American philosopher Hilary Putnam, and in his 1981 book Reason, Choose, and History. But the germ of this idea has been much longer, which given by Rene Descartes, and he gave the evil demon hypothesis in 1941, and I say that I should suppose that some malicious demo of the utmost powerful and cunning has employed all his energies in order to deceive me, and I shall consider myself as not having hands, or eyes, or flesh, or blood, or senses, but as falsely believing that I have all those things. And the modern counterpart of the evil demon hypothesis is the Brain-in-a-vat hypothesis. In this scenery, the evil demon is replaced by a mind scientist, and he removed people's brain from their skull and stored them in his labs, and each brain was connected to a super scientific computer. So this video is 3 here. Thank you.
Hello. Who are you? I am the architect. I created the Matrix.
So this one maybe is a mind scientist. He created Matrix, and all these videos are from the movie, The Matrix. So you probably don't believe that your brain is an event, and most people don't believe that. And most philosophers who give this argument probably don't believe that they are brain event either. But you don't have to believe that, because you have only to admit that you cannot be sure that you are not a brain event. And the problem.
Oops, seems that we had a connection issue.
So if there are no questions, I would probably close the session and these 5th ShanghAI lectures. So thank you all, thanks to the speakers, and thanks to the attendees for participating in different waves. So thanks all, and see you next time, next week, for the 6th lecture. Bye-bye.
Bye.
Yes, thanks a lot for your participation, and see you next week.
And then